It's my pleasure to welcome the last speaker of today. It's Dasha Semochkina. She's talking about AI accelerated or enhanced Bayesian experimental design for reaction kinetics. Thanks.
Thank you very much. And I want to thank the organizers. I really enjoyed this week. This is my first time here. It was great. I really enjoyed it. So this work is a collaboration between us and Southampton. So I'm working with Dave Woods, and we have some chemical engineering collaborators here in Cambridge. This work started off talking to them through how the process works. So the stages that they go through are usually the following. They do something in the lab. They're like, well, that's interesting. And then the idea is to scale this to big manufacturing level. But to do that, they need to first find a model that describes the chemical process well. They do have a big project that when they're working on automating this, they're working on model ontology. So they want some sort of big library that can automatically offer you some models. At the moment, they just go to an expert and say, what do you think is a good model for this? They can give them a couple of options, and then you need to calibrate those models well. And to calibrate those models, you want to collect some data, and this is where design of experiments could be useful. So this is where we kind of come in to collaborate with them. And as soon as you have the model and you calibrated the model, then you can move to a big scale manufacturing process, a bit more safe. So this is the model that they gave us. This is a process of one component reacting into 4 other ones. And as time goes by, this one is kind of going to 0 and the other one stabilize at a particular level. A set of differential equations that describe that. So we have concentrations of component A to E. And I'm just going to call that vector X. I'm just going to carry this for the rest of the presentation. So X is the vector of concentrations. So what do they do currently to estimate parameters that they're interested in? They want a reaction to go slowly enough so they can collect data. So if it reacts immediately, there's just no data, so they can't collect any kind of useful information there. If it reacts too slowly, there's also no movement in those curves, so it's also useless. So they want to find somewhere in between when the reaction goes slowly enough, but they don't really know how to get it, so they usually just guess a few settings in the lab that they can run the experiments at and collect data, which is somewhat sensible. And the question is, can we do better? So the goal of our work is to find optimal experimental design for something that they can control in the lab. In that case, I'm going to talk about temperature, so they can control temperature in the reactor. And could we find the optimum temperature so that when they collect the data, they can calibrate the model with the highest precision. So the data that they collect is the most informative. We started with this paper by Duarte et al., and they've done some optimal experimental design for linear, time-invariant state space models. I'm going to show in a second that ours is not linear in the controls. And therefore, we can really use some clever linear algebra tricks that they've used in theirs. And we also want to be Bayesian. They haven't done the Bayesian bit. So just kind of a few technical preliminaries. So this is our differential equation. I write it down as like a matrix form and the vector. So A is my matrix, which is parameterized by those parameters K from 1 to 5. And X is the vector of concentrations, and each parameter is parameterized by something that they want to calibrate. So those Ki zeros are the ones that they want to calibrate, times the exponential of the minus of this fraction where this is known, and T, the big T, is the temperature. So you want to find the optimal temperature so that they can calibrate those parameters well. And you can solve this analytically, and this is where I thought, oh, great, I've solved this analytically, what can possibly go wrong? But things did get wrong after that. And I have little t here represent time. So time goes forward, obviously, and the big T in here is the temperature. And you can see that this kind of parameter here depends on temperature, not linearly. Just to kind of write it down in a more generic way, I kind of want to have 5 concentrations to be written down as vectors, but then also the observations come as time points. So it's a matrix. Then we have our, I think, rows are the concentrations. Rows are concentrations and columns are the time points. And if you say that the model representation is that our measured response is equal to the true process states times plus some error term. And I want to write down this error term as matrix normal distribution, where you have zero mean and you have two variance-covariance matrices, one for time points and one for different concentrations. And the idea is that if you measure time points of the same experiment, they're not independent. So in terms of collecting information, it doesn't contribute independently to the information gain that you're trying to kind of look at. And to kind of vectorize this, you can just take the Kronecker product of those two matrices, and then the vectorized log likelihood would be proportional to this, but we're actually just interested in this bit in the middle, because if we need to take sensitivities to the parameters, this is the only term that actually depends on those parameters we're interested in. And I guess the methods that they're usually using currently, they don't really exploit correlations or dynamic control. So dynamic control is when you can dynamically change temperature in the lab in case that does better than just running the experiment under one temperature. I also want the covariance to be only present when it's kind of the same experiment. So if I'm looking at a covariance between a concentration I at time tk and concentration J at time TL, that exists, but only if the temperature is the same. If it's different experiment under different temperatures, there's no correlation between those data points. Okay, so as I said, we want it to be Bayesian, and everybody in the area is doing a de-optimality. So we just looked at the de-optimality criterion. So we want to calculate the expectation of the log of the determinant of the fish information, given some prior assumptions on our parameters, and we want to maximize that. We have solution to our differential equation, which is available again to us in closed form, and we can write down this fish information as just the derivatives with respect to parameters of interest, and we need the quadratic form of that. We can assume that we can allocate experimental budget proportional to some weights Wi, and give those different experiments to different temperatures. So we can assume that either we can change temperature within one experiment, or we can assume that we have a budget for 10 experiments and we can allocate different temperatures to different temperature settings. And all we need to do is to solve the system of differential equations, compute the sensitivities, calculate the fish information matrix, and then optimize this in terms of our temperature T. Why did we decide to be Bayesian? Because most of the practitioners, as I mentioned, they do kind of just select one parameter value and optimize temperature for that. And I guess if you look at the way that this Ki is parameterized, those two are interacting. So if you select one of them and you can optimize T and then select a different one, it can be quite a different optimum. So we kind of thought maybe we should make it a bit more robust in terms of maybe they don't know what the prior distribution is, but at least they can give us like an interval saying like it's somewhere over there. Can you make sure that if we guess wrong, or we don't have to guess, I guess, because if we do guess wrong, then maybe we optimized something which is quite poor in terms of collecting the data. And because I guess there's a lot of numerical integration, because yes, I can solve the system analytically, but I can't calculate the expectation analytically. So you need to do a lot of quite slow numerical integration. So what do we do? Of course, we use Bayesian optimization, because that's the first thing that kind of comes to mind to kind of just try to see if it does any good. So just a very quick kind of crash course on Bayesian optimization, and it's an emulation-based approach that tries to fit a surrogate model to the process. that you're trying to optimize, and it fits better when you have some observations, and it's less certain in the area where you don't have any observations. And if you're trying to minimize something, you kind of look at the current minimum, you look at the Gaussian at each point, which is centered at the mean prediction, you look at the tail of the Gaussian and try to integrate out the potential difference between the current optimum and what you can improve on, and kind of gives you the measure of what your expected potential improvement could be. And the idea is that you can have very few training points originally, and they'll be rubbish in most places, but it'll get very quickly to something that is optimum, so you don't have to spend an awful lot of computational budget exploring everywhere. So I've started off with the simplest case. I've looked at flat priors, just one temperature setting, and independent outputs. So I didn't look at the correlated output at all. I fitted a Gaussian process. I think I fitted about 10 points, which I think was an overkill. So 10 equally spaced points here, and then I let it to run for 10 more sequential points. So those orange dots here are the points at which it's selected to sample. And you can't really see, there's a tiny bit of uncertainty there left in the right corner, and everywhere else the Gaussian process is fairly certain. And they seem to have identified two temperatures that are optimal. One is around maybe 475, 480, and then one around 600. And those two peaks are about the same height, so both of them are optimal. And that's, of course, when I've done flat priors, and then I was like, what happens if I have something more intelligent or more informative? If you fit gamma prior, and the shape was exactly the same, but this kind of scale on the y-axis kind of changed, but the shape of the d-optimality curve was the same. Which is kind of the point that the Duarte et al. Paper had, because they said, oh, we've selected a parameter value and we've optimized for our controls. And when we selected a different parameter value and we optimized control, and they don't look that different, so maybe it doesn't matter. Well, maybe, I don't know, maybe it doesn't matter. I was a little bit disappointed, but I'm keep thinking about why it doesn't make a difference in this case. Of course, as I mentioned, there's a lot of numerical integration, and one bit that I didn't account for at first is when you calculate a derivative of a generic k-dependent exponent ak, it is actually not a derivative. Well, it's a derivative, but it's another integral that I need to calculate numerically. And we're being Bayesian, so there's a lot of numerical integration that I have to do. So then I wanted to kind of look at increased complexity, where I extend to multiple temperatures and I include some correlations. So just to kind of remind ourselves about the matrix normal error term, where we have a covariance for the time points and a covariance for different concentrations. And they only exist when the temperature settings are different. Right, and because there's a lot of numerical integration, I had presented a poster a couple of years ago, and Darius Jushinsky came over to me and said, why don't you just do a direct method? I didn't know what that is. So he was like, yeah, there's a good book that kind of describes how to do it. So all you do is you take the original differential equation system, and then you differentiate it with respect to your parameters of interest, and then you need to know the differential with respect to initial conditions, and then you solve the extended system, and it's much quicker because you differentiate rather than integrate, and that's quicker. And he said you only need to do it once, and then it's very quick. But in that case, the case he was talking about, he was optimizing in the same space as the parameters are, and I'm optimizing in the control space, and the parameters are separate, so I do still need to do it multiple times. But it is quicker than just solving the system first and then trying to take the derivative of the solution of the differential equation. And then I kind of thought, okay, but I still need to do a lot of integration. Is there any way I can kind of avoid that? And I looked at different versions of the d-optimality criterion. So the one on the top is the original one, where you take the expectation of the log of the determinant of the, inverse of the fish information. But Atkinson's book with the design of experiments with SAS has a chapter on Bayesian design, and it talks about 5 different versions of de-optimality criterion. And one of the other ones is this one, where you take the expectation inside. So you take the log of the inverse of the determinant of the expected fish information. And for the purpose of the general equivalence theorem, if you look at the directional derivatives of this criterion and this criterion, so nk here is the number of parameters. You can have nk minus the expectation of the trace of the product here, where this is the fish information, and the second term is the elementary information matrix that corresponds to a design point with design with 1 support point. And they kind of look similar, but they're not exactly the same, right? So the trace is linear, so you can maybe exchange trace and exponential and take it inside. But they still kind of, it's not exactly the same. It could be the same under some conditions. But in general, because you kind of take the expectation here, this design will say, if on average we're doing okay, I don't care for the individual contributions as much. But this one does care more about individual contributions. This would probably potentially be more concentrated, and the other one might give you more dispersed points. Excuse me. But hopefully, if you can utilize the direct method and just switch to this criterion, you can do this much quicker inside and then just take the log of this just once at the end. And it is much quicker than just doing going forward the original way. So we can solve the ODEs directly, which is faster than calculating the sensitivity through analytical expressions. It allows optimization for fish information matrix more efficiently, and the log determinant switch kind of reduces the computational load. But how does that compare? So I decided to just brute force this with particle swarm, so I didn't fit any GPs. I had flat interval priors. I've done the direct method when I extend the system of ODEs and solve it. And I've used the second version of the de-optimality criterion. And it converged to something like this. And if you remember the first one I got, you can see that the values are actually very similar to the optimum over there. So I have one which is kind of over here, and the second one is kind of over there, which was both disappointing and encouraging. And I guess encouraging is because, well, I guess maybe it's doing something sensible, but disappointing is, well, I've added kind of correlation in the output space. I've kind of combined things. I've did a different criterion. Why is it kind of giving me the same points? I don't know. I don't have the answer yet. I'm still processing. And the kind of slightly more advanced setup that we looked at, and that is when it's more interesting to us as mathematicians and statisticians. But if you go to like chemical engineers, they're like, we can't actually do that in the lab. But we still decided to kind of explore that a little bit to see what happens. And we decided to look at what happens when we could change temperature dynamically during the same experiment and allocate different proportion of the experiment to different temperatures. So we've selected three temperatures and 3 weights within the same experiment. So this is the kind of the output that I got. So I used Gaussian process Bayesian optimization for this. So I have one temperature here, and then the length of that interval is kind of proportional to the weight that was allocated to that temperature. Then it goes up and then it goes down. And here on the right, I've decided to plot, I think the first 20 points are the space fit and design to train the emulator. And then the next 20 points are the Bayesian optimization steps. So I think this one was the best design that it found. And here I decided to plot what happens if you randomly select 3 temperatures and randomly allocated 3 weights. And the black line is the median, and the shaded gray area is the 50% confidence interval, which is, it's not doing amazingly, but it is doing slightly better. And if that's something that they will be open to explore in general. I know like the temperature wouldn't switch like this, so we would have to kind of input some smoothness there that kind of goes up and down more smoothly. Some correlation there as well, which is something we're currently exploring. So just to kind of sum this up, what I want to do next is I want to see how well the GP-based and the particle swarm optimization scales to kind of slightly more bigger problem, explore more differences between the versions of de-optimality and kind of see where it breaks a bit more obvious, and extend to more control variables. So no, only controlling temperature at the moment, but they are interested in having more control variables to optimize. And next week, I'm actually going to this conference that they organized here in Cambridge. It's called AI for Biochemical Engineering. And I'm going to talk to them. And hopefully, they're not going to tell me that I did it all wrong and that's not what they meant. But we shall see. And next week, we're going to find out. And thank you very much.
Thanks so much.
Thank you.
We have some time for questions.
Hi. So I was wondering if temperature is the only thing that can be controlled for this experiment? Because
For this system in particular, I think they said they can control initial conditions as well.
So if you fix the initial conditions and only try to adjust the temperature,
Yeah.
you will get one experiment, like one optimal design.
Yeah, yeah.
But if you try to have everything flexible,
Yeah.
how different would that optimal design be? Where
That is one of my next questions. Yeah, this is interesting. It is heavy enough to optimize, so I'm a little bit scared going into, because especially if you have, well, I guess in that case, it's not very interesting because the system is that everything starts in one component and reacts into the other one. So if it's just, you're going to be changing just this, so it's going to be going up and down, everything else starts at zero. So maybe for that particular system, it's not very interesting. But in general, they are interested in controlling more things, yeah.
Further questions?
Right, so you're using the optimality
Yeah.
sort of as a criterion, but there are many other approaches, right? If you have if you put some prior over your parameters, you can use information gain and so on and so forth. Can you give any insight why the optimality?
That's a question they get a lot, and the silly answer is that because Duarte paper used the optimality and we wanted to extend what they've done. A slightly more intelligent answer is that practitioners get very scared if you push them too far. So they know the de-optimality, and I kind of want to kind of extend it a little bit more. If you start saying that this is wrong and this is wrong and this is wrong, I mean, it's interesting from our perspective because it's a better measure, right? It's a better measure of information gain. But from practitioners' perspective, they're like, I don't want to explore it too far, you know.
Further questions?
Maybe I can ask another question. So I was wondering about noise, because reactions are noisy and you're getting a lot of noise. And you're here, for you the noise is just like Gaussian observational noise, right?
Yeah.
Because I think you can model reactions with stochastic differential equations and stuff like this, which would give you different noise. And maybe if you have the mismatch between your noise distribution and actual noise, maybe there's something.
So you mean model the whole reaction with the stochastic differential?
So in the reaction network, there's people are sometimes modeling with more not with ODEs, but with for example Markov-Chain processes. You can somehow write some probabilistic version of that. I'm not exactly sure how it works. There's something I think called Langevin approximation, which allows you to sort of write all of those reactions, including some noise that is like.
But then again, you'll have to convince the practitioners that this is the better way to model things.
I see.
They're a bit conservative.
I see. Thank you.
Any further? I have a quick question. It seemed like you found in both methods like two optimal designs actually, right? The two T's. Can you say perhaps something a little bit more on how
because you'd expect
what
maybe
it all means?
5 of them, right? You have 5 parameters, you expect 5 maybe optimum or some.
Why are the things in between slightly less, like there's a dip, right? So somehow...
I don't know. What I would say is, I think that some parameters are dominating the sensitivities. So I don't think they're all contributing equally. But in a way, I don't know.
Okay, okay.
But I think one or two of them is like if you take the sensitivity and you plot it, it's like orders of magnitude away from everything else.
Okay.
So maybe.
Have you looked at the posterior that you get, actually?
Which side?
Have you looked at the posterior? So now you have done the experimental design. You could, in a way, emulate, let's just put in some parameters in the system and then, well, run on your computer the experiment and then you do the inference as well.
You mean with the kind of parameter input being uncertain and see
Exactly. So computer,
No.
yeah, so you have your prior.
Yeah.
You now know, okay, I should do this experiment, but you could now emulate on the computer what actually you could get.
No, I haven't.
So like that, you could see actually how different the posteriors.
That makes perfect sense. Yeah, I should do that. Thank you.
Okay. Last question maybe from me. Why is the scale 10 to the power of 35? Is that a concern?
Yeah. But as I said, like when I did gamma priors, sorry, and rather than flat ones, I think it went even like, well, the power went higher, but the shape was the same.
Okay.
So I think it's like it's a numerical thing somewhere in the integration, which kind of gives it.
Okay.
And I think actually, if you do the direct method, where you take the expectation before, it gives you this, well, actually I haven't tried the full GP, but it's on a very different scale, and I think the scale is because this is first and then the log kind of like puts it down a little bit, where this one is, I think, kind of blows up in some way.
I mean, it could be that in a way, right, because you do take the determinant
Yeah,
and so on. So maybe if the matrix is not well conditioned, some eigenvalues are close to zero, you run into these issues. Where perhaps then, the lower bounds of mutual information may be then the better choice because they would handle that perhaps more closely.
That makes sense, yeah.
Any more questions? If not, let's thank Dasha again.
Thank you.